So, I handed out in class today a review thing for the midterm. So I shorted your table by 1. Do you want a paper copy?
Should be fine.
Okay, there are people who aren't here, and you're the only person who didn't get a paper copy, so I have one for you. Okay. Cool. So there's those to think about. They're posted to the web page also. The version posted to the web page doesn't have that silly typo that I've crossed out somewhere near the bottom of the page. Groovy. So here's what today's going to be. I have one result left to prove from the notes from last time. And then the only thing left in this packet is a group walk, which you might be able to flip open to before I can flip a page, in which you will prove an important theorem in analysis called the nested intervals theorem. So we'll build up to what it says, and then I'll just be quiet for the last, ideally at least 45 minutes of class. And you all will work on that, and that will be the homework assigned today, completing those. Cool. So let's get started. So here is the last result left to prove using the same philosophy as monotone convergence. Consider any set which is non-empty and bounded above. Any such set admits a sequence, x sub n, which satisfies some conditions. For every natural number n, x sub n is in the set x, so it's a sequence of elements of the set big X. And xn converges to the supremum of the set big X. Hopefully that seems believable. Right, like, there's the number line, there's the supremum, there's the set. This just says that you can find a sequence of elements of the set that get close to the supremum. So let's try to prove that. And the proof, I think, will be reasonably straightforward. So let's let x be the supremum of the set big X. I will take epsilon n to be 1 over n. Using the reformulation of the supremum involving epsilons, we see that there is some x sub n in the set X such that some stuff happens. So what did that reformulation in terms of suprema in terms of epsilon say?
I'm not sure. Where is it?
It's way back in the section on completeness.
Oh.
So let's just draw a picture of what it says. So this isn't going to be the proof of the theorem, but it's going to be how to remember the statement of the theorem. Can make this shot. Holes on it. I appreciate that. I thought you were going to show me hands on. So if there's the supremum, it's called x right now. Could x minus epsilon possibly be an upper bound on the set big X? From that, it follows there is some element of the set which is in this range. So that's what I'm going to write down. Let's let epsilon n be 1 over n. Using the reformulation of the supremum involving epsilons, we see there's some xn in the set big X such that x, the supremum, minus epsilon, which right now depends on the choice of n, is less than or equal to xn. That's the element of the set big X. Oh, and that's a strictly less than. Doesn't matter, but it is. Less than or equal to X. Cool. People happy so far? All right. So let's now just check that this sequence does everything we want. Let's consider the sequence xn consisting of the elements of X we just found. Maybe I'll also rewrite that a little bit. So, since epsilon n equals 1 over n, x minus 1 over n less than or equal to xn less than or equal to x. So we need to show a few things. We need to show that xn converges to x. And here's like an epsilon n argument, but maybe I'll use a different one. So maybe ignore everything written after that point. If you knew this was true for absolutely every natural number n, and you wanted to show that x sub n converged to x, what's one way you could do that without any epsilons showing up at all? Yeah.
Find the limit of the left-hand side.
Find the limit of the left-hand side. What's the limit of the left-hand side?
X.
Cool. What's the limit of the right-hand side?
X.
So what does the limit of the thing in the middle have to be?
X.
Cool. Let's write that down. We must show xn converges to x, so I'm going to cross that out. I'm just not going to use it. We will use the squeeze theorem. So you told me the thing on the left goes to 0. Give me just like a one-sentence reason why the thing on the left goes to 0. Nope, goes to x. Yeah.
I guess as n gets bigger, it gets whenever n gets closer to 0.
Yeah. So I'm going to say that as follows. So since limit of 1 over n equals 0, it follows that the limit of x minus 1 over n equals x.
Did you also appeal to the definition of a limit over there, or would that just be too much?
If you wanted to appeal to the definition of the limit, you would have to compose an epsilon n argument, because that's what using the definition would mean. I want to use, instead, the fancy tools we know about limits.
Okay.
Right? We have limit laws. We may as well use them. It wouldn't be that hard to come up with an epsilon n argument for the whole thing to begin with. Yeah, I guess if you wanted to prove this by an epsilon n argument, you could. But I feel like we've probably achieved that goal at some point in the past. We could probably cite something, but I think that's a limit that we're allowed to know. All right. So, similarly, why is the limit of the thing on the right-hand side equal to x? Yeah.
Because it is x?
Yeah, it's a constant sequence. As x is a constant sequence, the limit as n goes to infinity of x is equal to x. Thus, by the squeeze theorem, the limit of x sub n is equal to x. And let's just check that we've done what we set out to do. Have we constructed a sequence called xn?
Yes.
Is every term of that sequence an element of the set big X?
Yes.
Yeah, right there. Does xn converge to x? Nice. As we have xn in x for all n in n, and xn converges to x, we have proven the needed result. I guess now there should be a square box. How low is Barrett? Cool. That both seem natural enough? Groovy. So, good. So the main point of today is the following glue block. All right, just write down some sentence that says you're done and why you're done, and then put the little box. The exact words don't matter; they're not magic. That last sentence.
What's the last word exactly?
Result.
Oh, I see.
Yeah.
Okay.
But similarly, you could use theorem or proposition or claim.
Yeah.
Groovy. So, here is the result of today, the nested intervals theorem. So the nested intervals theorem says this. Suppose that I1 contains I2, contains I3, contains I4, is a sequence of nested closed, bounded intervals, then the infinite intersection of them is not empty. So what this says is if you have a bunch of closed, bounded intervals, and they keep getting smaller, even though they keep getting smaller, they can't get rid of everything. There will be something in the infinite intersection. And that might not seem like an exciting result right now, but it would fire a way to constructing lots and lots of different things. If you have a single thing that is supposed to happen for some infinite collection of things, we'll just get it to happen for the first finitely many and find that that's a closed bounded interval. Get it to happen for the next bunch. That's another closed bounded interval. If you can show that, and these closed bounded intervals are all nested, then the thing in the infinite intersection is the thing you're looking for which this thing is true for absolutely every natural number. That's very vague. We'll use this trick at some point in the future. So let's expand out what this means. It's going to be hard to prove it if we don't know what all the words mean. So first of all, recall that for any real number is a less than b, where a less than b is boxed, for emphasis. The closed bounded interval from a to b is defined by bracket a comma b bracket is equal to, what's the closed interval from a to b? In like set builder notation? It's the set of all x. Well, no, so I just said like what the name of the element of the set's going to be. Is something over here in that closed bounded interval? Oh no. Is something in between a and b in that closed bounded interval? Yeah. So I'm like an inequality, right?
Yeah.
What inequality do I want to write?
It would just be like a is less than or equal to x, less than or equal to b.
Awesome.
Totally okay,
Right. That's all I wanted. Maybe just for comparison, if that's the closed bounded interval, what's the open bounded interval given by? Yeah.
So just the same things with strict inequalities, so like knowing is less than x is less than b.
Yep. All right, next thing. So suppose you have a sequence of intervals. So a bunch of intervals, each one's indexed by a natural number. So there's I1, I2, I3, I4. Each one of them is an interval. These things are called nested. If I sub n plus 1, that's the opposite of nested. I sub n plus 1 is a subset of I sub n for every natural number. Okay. The intervals keep getting smaller. That's what the word nested means. And the final thing is, what the heck does that infinite intersection thing mean? So we know how to intersect like two things. That's all the things that are in both of the sets. If you can intersect two things, and you can intersect three things by doing the intersections like one at a time, but that'll only get you finitely far. What does the infinite intersection mean? And here it is. For a bunch of sets, A1, A2, A3, so you have some sequence of sets. The infinite intersection of those is the set of all things called A right now, which satisfy that for every natural number n, A is in the set A sub n. Does that seem like it's what the infinite intersection should mean? It's the set of all things that are in absolutely every one of those A sub n's? Yeah.
I'm not sure if I quite understand that phraseology. So to rephrase a little, is it just like the like I said, a subset of all elements that are shared by all of the sets?
Yep.
Okay.
Yeah, and that's what that should mean. So let's put that into words. So A in the infinite intersection means, so this is the definition of the thing, A is in AN for every n in n. That seem right? And that's what the infinite intersection should be. You should be in absolutely every one of the sets these sets happen to be indexed by a natural number. So, as a warm-up, here's a thing to prove. The infinite intersection of the sequence of closed bounded integrals with n times 0, 1 over k, where k is a natural number, that infinite intersection is equal to the set containing only 0. So I guess first things first, do you believe that? Tell me why you believe that. Like what's the informal argument you have in your head? Almost anything can be right now. Yeah. I said.
We know that A exists, right? That's the one thing. Like we know that it's not. We know that A is not empty itself.
What do you mean by A right now?
Some element that is at the intersection of all the
Okay.
capital A sub x.
Sure.
We know that that's something by some relative assumption.
Well,
It's
that's
not
the thing that
the
we're going to
empty set
prove later.
Okay.
But okay, so it has something in it.
Sorry.
No, you're good. So let's try to maybe jump straight to proving this formally. How do you prove two sets are equal?
You prove that it's got to be a subset of the one and go backwards if the other one has to be a set of the other?
Yeah. So I want to quit before the 25-minute mark, certainly, so that you have time to do all this. So I think I'm going to be on the board, and we'll be a little bit informal. Cool. So, let's try to sketch the proof. So, the set containing only 0 is equal to the intersection from k equals 1 to infinity of 0, 1 over k. Here's the thing we want to show. As you said, I think we need to prove two containments. So, which one seems like it's more obviously true? We'll try to do that one first. There's no right answer here. Yeah.
I'm going to go from the infinite intersection side equaling 0.
Cool. So, that would be this containment. So, how do you prove this is contained in that? You should consider an element of the little R set, show it's in the big R set.
Should we be writing this particularly down in the notes, or is there going to be like a more formal, like, right up, which is what you done?
You can write this at this point. I may not be totally formal. Yeah, screw it. I'll just write right there too. So, first, show the infinite intersection 0, 1 over k is contained in singleton 0. To do that, we let A be an element of the infinite intersection. Cool. All right. So we want to get that A to be in the set containing only 0. Let's just get our want to show clear. What does it mean to be in the set containing only 0? What's the only element of the set containing only 0? 0. So we just need to show that A is equal to 0. So let's try to do that, and let's start by parsing this out. What does it mean to be in that infinite intersection? Yeah.
It means that all elements of that resulting set are in all of the subsets? Or all of the sets that the thing shows?
So this A should be in every one of those sets. Yeah. So A is in 0, 1 over k for all k in n. Nice. What does it mean to be in the closed interval from 0 to 1 over k? Yeah.
that 0 is less than or equal to a, which is less than or equal to 1 over k.
All right, we want to show that this sucker is equal to 0. What ideas do you see? How would you want to do that? Yeah.
Squeeze Theorem?
Great, yeah. What's the limit of 0 as k goes to infinity? What's the limit of 1 over k as k goes to infinity? The thing in the middle is a constant sequence also, so it is equal to its own limit. So I think I would be happy now with just the sentence by the Squeeze Theorem. A, which is the limit of a as k goes to infinity, is equal to 0. Groovy. So, have we now successfully proven one of the two set containments? Yeah. Thus, the infinite intersection is contained in singleton 0. Let's go the other way. So I guess that means we need to consider any element of the set containing only 0. What's the only element of the set that contains only 0? 0. So I guess we need to show for the opposite containment, we need 0 to be in the infinite intersection k equals 1 to infinity of 0, 1 over k. And now maybe I'll go to the board and expand this thing that we want to show. All right. So this is the thing we want. What does it mean to be in that infinite intersection? What does it always mean to be in that infinite intersection? Yeah.
That all of your elements are contained in everything, in all of those other sets.
That
So 0 is in all of those.
Yeah. Okay. So, what does that mean? Well, I think it means like there's our goal, so let's try to use this argument. Yeah.
So then we know that 0 is less than or equal to 0, which is less than or equal to 1 over k.
Is that true?
Yes.
Yeah. Nice. So now we know what we need to show. Well, let's do that. For any k in the naturals, 0 is less than or equal to 0 is less than or equal to 1 over k. So 0 is in 0, 1 over k. Thus, 0 is in the infinite intersection. How'd that proof feel? It went fast, but yeah.
So the second line of the board, that's just from like the definition of the function of the board.
From there?
Yeah.
Yeah.
And then the bottom part's the Squeeze Theorem.
This bit is just true. Yeah, so 0 is something less than or equal to 0. For every natural number k, 0 is less than or equal to k. So there's no squeeze theorem at all there. We use the squeeze theorem in the opposite containment. Nice. All right. So the point of that exercise was to get you used to what it means to be in an infinite intersection. Yeah.
Should it be 0 as a subsection of the infinite interval? That way we prove the second thing.
If you really want that, then you need to write a set.
I don't know if that's required or not.
I didn't write a very good closing statement, so, consider writing a better closing statement than I did. Cool. So, here's what the remaining time is for. The proof of the nested intervals theorem. I'm going to flip the page. Cool. You will complete the proof of the nested intervals theorem. So start with the setup. Suppose that you start with a sequence of nested closed intervals. Let's put the word bounded there too. So that means that for every natural number n, In is a closed bounded interval, so In is equal to some An comma Bn. For some choice of An and Bn. And here are the steps that I'll have you do. First, use the fact that these intervals are nested to get that inequality to follow. Use that to conclude that the left endpoints, the ANs, form an increasing sequence, the right endpoints, the BNs, form a decreasing sequence. Well, we're going to appeal to monotone convergence. Once you have an increasing sequence and a decreasing sequence, you just need some bounds. Prove that B1 is an upper bound on the ANs, A1 is a lower bound on the BNs. Make a conclusion by monotone convergence. And then you'll basically be done. So, I'm going to be quiet now. Talk with each other. You can maybe even move because, well, you might want to move. You don't actually have a group to walk with it if you want to walk with anyone. Cool. So I'll have you start discussing at this point with each other. I will also now stop recording.
So considering